Planet Semicon welcomes you to explore the field of semiconductor physics and technology, the foundation of microelectronics and VLSI design engineering.
In this presentation, we will review the influence of unavoidable semiconductor process variations on physical layout design. We will also review how these process variations are translated into physical layout design rules. These design rules help ensure that the fabricated devices achieve the intended electrical characteristics and performance. Ultimately, adherence to these rules contributes to improved manufacturing yield and reliable semiconductor production. So let's get started. Semiconductor technology has evolved from individual semiconductor devices to highly integrated circuits containing millions or billions of devices. The development of planar processing and photolithography made it possible to fabricate these devices repeatedly on the same silicon wafer. As integration increased from ICs to VLSI and ASICs, the dimensions of the physical structures became progressively smaller and more tightly controlled. Every fabrication step contributes to the final physical structure of the device. These physical dimensions directly influence transistor parameters and, consequently, circuit performance. Therefore, modern ASIC manufacturing depends not only on the circuit design itself, but also on the ability to reproduce its physical dimensions accurately, repeatedly, and at high volume. This forms the basis for understanding process variations and the need for design rules and physical verification. Semiconductor manufacturing has progressed from producing individual semiconductor devices to fabricating highly integrated circuits containing millions or billions of transistors. A major step in this evolution was the development of planar processing, which allowed multiple devices to be formed on a common silicon wafer. Photolithography further enabled complex patterns to be reproduced accurately and repeatedly across the wafer. By combining lithography with processes such as oxidation, implantation, etching, deposition and metallization, multiple device and interconnect layers can be built sequentially. This makes it possible to manufacture a large number of identical circuits simultaneously, providing the throughput and repeatability required for mass production. The same fundamental approach supports modern IC, VLSI, and ASIC manufacturing. However, as integration and device density increase, even small fabrication variations become increasingly important to device performance and manufacturing yield. The semiconductor fabrication process begins with a high-purity silicon wafer, which provides the starting substrate for device fabrication. Next, different materials such as oxides, dielectrics, and semiconductor films are formed on the wafer to create the required layers. Photolithography then transfers the circuit patterns onto these layers using masks and photoresist. The selected regions are subsequently etched or implanted to form the required device structures. Additional materials are deposited and planarized using CMP as successive layers are built. Contacts and metallization then establish the electrical connections between devices and interconnect layers. Finally, the completed wafer undergoes passivation, dicing and packaging, converting the fabricated wafer into individual semiconductor devices such as ASICs. This flow diagram expands the previous overview by showing the major fabrication stages in their sequence. The wafer first progresses through cleaning and layer formation, followed by repeated cycles of photolithography, etching, implantation and annealing to build the device structures. Deposition and CMP are then repeated as additional layers are formed and planarized. Once the front-end device structures are complete, the process moves to the back end, where metallization creates the required interconnect network and passivation protects the completed structure. The wafer then undergoes electrical testing, dicing and packaging, followed by final testing. The key point for our discussion is that each of these stages has its own process capability and sources of variation, which can ultimately influence the physical dimensions and electrical behavior of the final ASIC. A CMOS inverter is not fabricated using a single pattern. Instead, multiple masks are used to define different physical layers and regions of the device. The well mask establishes the well regions required for the NMOS and PMOS devices. The active mask defines the regions where the transistor source, drain, and body structures will be formed. The gate mask then defines the gate geometry, including the critical channel dimension. Additional source and drain patterning is used where selective implantation or doping is required. After the devices are formed, the contact mask defines the openings through which the device terminals are electrically accessed, while the metal mask defines the interconnections between them. By applying these masks sequentially, the individual physical layers are aligned and combined to form the complete CMOS inverter. Photolithography provides the essential link between the circuit layout and the physical structures fabricated on the semiconductor wafer. The required circuit geometry is represented on a mask or reticle and transferred to a wafer coated with photoresist. During exposure, the optical system projects the mask pattern onto the resist. Development then creates a patterned resist layer that selectively protects or exposes regions of the wafer for subsequent processes such as etching, implantation or deposition. This sequence is repeated for different fabrication layers, allowing complex CMOS devices and interconnects to be built layer by layer. Because lithography defines dimensions such as gate length, line width, spacing and contact geometry, its accuracy has a direct influence on the final physical dimensions, device characteristics, manufacturing yield and circuit performance. A photolithography system consists of several precisely controlled components that work together to transfer a circuit pattern onto the semiconductor wafer. The light source provides the radiation required to expose the photoresist. The mask or reticle contains the pattern representing the required circuit geometry. An alignment system ensures that this pattern is accurately positioned relative to the structures already fabricated on the wafer. Projection optics focus and typically reduce the mask pattern before transferring it to the wafer surface. The wafer stage provides precise positioning and movement during exposure. The photoresist-coated wafer receives the projected image, and subsequent development converts the exposed resist into a physical pattern. This patterned resist then acts as a temporary mask for processes such as etching or implantation. Thus, the lithography system controls both where the pattern is placed and how accurately its dimensions are reproduced. Mask pattern transfer is the fundamental sequence through which lithography converts circuit geometry into physical semiconductor structures. The process begins with a mask containing the required pattern for a particular fabrication layer. The wafer is coated with a uniform layer of photoresist, which is then exposed using the mask pattern. After development, selected regions of the resist are removed, leaving a patterned resist layer on the wafer. This resist pattern then controls the next fabrication operation. For example, exposed regions may be etched away, or selected areas may receive ion implantation. Once the required process is completed, the remaining resist is removed. The same basic sequence is repeated using different masks to create successive device and interconnect layers. Therefore, lithography does not itself create the final semiconductor layer, rather, it precisely defines where the subsequent fabrication process will modify the wafer. Photolithography introduces two important categories of physical variation: critical dimension variation and overlay variation. Critical dimension, or CD, refers to an important physical dimension of a patterned feature, such as a gate or metal line width. The actual printed dimension may differ from the intended value because of variations in exposure, focus, photoresist behavior and other process conditions. The pattern can also experience distortion, causing its shape to differ from the original mask geometry. Overlay variation is different. It refers to the positional misalignment between the current pattern and features created in previous fabrication steps. Exposure dose and focus variations can contribute to both dimensional and pattern placement errors. These variations are important because they transform the ideal mask geometry into slightly different physical dimensions on the wafer. Those physical differences can ultimately affect transistor parameters, circuit performance, and manufacturing yield. Process variations are unavoidable because semiconductor manufacturing involves many physical processes, materials and equipment, each with finite accuracy and repeatability. Lithography tools, etching systems, deposition equipment, implantation systems, and CMP processes cannot reproduce exactly the same result every time. In addition, the properties of wafers, films, photoresists and other materials vary naturally. Some variations occur from wafer to wafer, while others occur across different locations on the same wafer. Temperature, pressure, gas flow, exposure dose, and process chemistry can also influence the final result. At smaller dimensions, even very small local or random variations can become significant. Therefore, semiconductor manufacturing is inherently statistical. Instead of producing exactly one physical dimension, it produces a distribution around a target value. This means that process variation is not limited to lithography, it is introduced throughout the entire fabrication process. The process distribution curve represents process variation through its standard deviation, sigma, indicating how closely fabricated devices meet specification, thereby influencing manufacturing yield. We have established that process variation has a statistical nature and that this variation influences manufacturing yield. The next question is where these variations actually originate. In reality, variation is introduced throughout the fabrication flow. Film formation processes can produce thickness and material property variations. Lithography can introduce critical dimension and overlay variations. Etching can change feature width, profile, and depth, while implantation can produce variations in dopant dose and junction depth. Deposition processes contribute film thickness and uniformity variations, and CMP can introduce thickness and planarity variations. Finally, metallization can introduce variations in metal dimensions and electrical resistance. Therefore, the final device dimensions are the cumulative result of variations introduced at many fabrication stages. Although lithography is critical because it defines the geometry of many semiconductor features, it is not the only source of process variation. Etching can introduce variations in feature width, profile, and depth. Deposition processes can produce differences in film thickness and uniformity, while implantation can cause variations in dopant concentration and junction depth. CMP can affect film thickness and surface planarity, and metallization can introduce variations in metal dimensions and resistance. These processes therefore contribute to the final physical characteristics of the device. The important point is that process variation is distributed across the complete fabrication flow, rather than originating from lithography alone. Process variation is introduced throughout semiconductor fabrication due to unavoidable differences in equipment, materials, and process conditions. These deviations from the intended process targets appear as changes in the physical dimensions and geometry of the fabricated structures. In lithography, CD variation can change gate length and line width, while overlay variation affects the relative alignment and spacing between successive layers. Etching can change feature width, depth, and sidewall profile, while deposition affects film thickness and uniformity. Implantation variations influence dopant concentration and junction depth, and CMP can change layer thickness and planarity. Similarly, metallization variations can affect metal width, thickness, and interconnect resistance. These physical variations ultimately modify important device dimensions and electrical parameters, providing the direct link from fabrication process variation to device and circuit behavior. Once process variations have translated into physical dimension variations, the next step is to understand their impact on transistor and interconnect behavior. A change in gate length, for example, modifies the effective channel geometry and can influence drive current, switching speed and short channel effects. Variations in gate width change the current carrying capability of the transistor. Similarly, variations in oxide or high K thickness affect gate control and capacitance, while junction dimensions influence the electrical behavior of the source and drain regions. Contact resistance variations introduce additional resistance between the transistor and its interconnects. At the interconnect level, variations in metal width and thickness change resistance and can also affect parasitic capacitance. These physical variations therefore translate directly into electrical parameter variations such as threshold voltage, drive current, leakage, resistance and capacitance. Ultimately, these parameter variations affect circuit timing, power, signal integrity, and overall manufacturing yield. The next step is to understand how variations in individual device parameters translate into circuit-level behavior. A fabricated circuit contains many transistors whose electrical characteristics may differ slightly because of the physical variations introduced during manufacturing. For example, threshold voltage variation can shift the switching point of a CMOS gate and change its noise margin. Drive current variation changes how quickly a circuit node can charge or discharge, resulting in propagation delay variation. Leakage current variation affects the standby power consumed by the circuit, while capacitance variation changes the charge required during switching and can influence timing and dynamic power. At the interconnect level, resistance variation produces changes in voltage drop and signal propagation. Together, resistance and capacitance determine RC delay and can influence signal integrity. Therefore, the variations that originate at the fabrication level eventually appear as measurable variations in circuit timing, power, noise margin, signal integrity, and overall performance. We have seen that process variations ultimately create physical dimension variations, which can affect device and circuit performance. Physical design therefore cannot use arbitrary geometries. Every semiconductor process has practical limits on how small a feature can be made, how closely two features can be placed, and how accurately different layers can be aligned. Minimum width and spacing rules provide sufficient manufacturing margin, while enclosure and overlap rules account for alignment and process variations. Contacts and vias also require adequate dimensions to ensure reliable electrical connections. For sensitive devices, additional constraints such as matching and symmetry may be required to reduce the impact of process variations. These manufacturing capabilities and limitations are converted into a formal set of design rules that guide physical layout. The layout is then checked against these rules before fabrication. In this way, design rules provide the bridge between semiconductor manufacturing capability and physical design implementation. We can now make the direct connection between semiconductor manufacturing and physical design. Every fabrication process has a finite capability and an associated tolerance due to unavoidable process variations. These manufacturing limits must therefore be translated into practical constraints for the layout designer. For example, a minimum line width ensures that a feature can be printed and fabricated reliably, while minimum spacing prevents unwanted shorts between neighboring structures. Enclosure and overlap rules provide additional margin against alignment and process variations. Contact and via dimensions ensure reliable connections between different layers, while metal width and spacing rules support manufacturable and electrically reliable interconnects. Density rules are also important for maintaining process uniformity, particularly in planarization processes such as CMP. These requirements are converted into formal design rules, which define the geometries permitted in the physical layout. Therefore, design rules provide the direct bridge from manufacturing capability to manufacturable layout geometry. This image illustrates the typical geometric constraints applied during physical layout. Minimum line width and spacing define the smallest feature dimensions and separation that can be reliably fabricated. Enclosure and overlap rules provide sufficient margin between interacting layers and account for alignment variations. Contact and via dimensions ensure reliable electrical connections between layers. The image also shows metal width and spacing requirements, which control interconnect manufacturability and reliability. Finally, density requirements help maintain uniform processing across the wafer. Together, these rules convert manufacturing capabilities and tolerances into practical layout constraints that can be checked by DRC. Once design rules have been defined, the physical layout must be verified against them. This is the role of design rule checking, or DRC. DRC examines the layout geometry and checks requirements such as minimum width and spacing, enclosure and extension rules. It also checks layer-specific requirements and density constraints that are important for reliable manufacturing. In addition, modern technologies may include checks for antenna effects and other process-dependent reliability requirements. When a violation is detected, the DRC tool identifies the affected location and the corresponding rule. The designer then modifies the layout and repeats the verification process. Importantly, DRC is primarily a physical manufacturability check. It determines whether the layout follows the geometric and manufacturing constraints of the technology. Thus, DRC provides an essential verification step between layout creation and fabrication. This table illustrates how fabrication requirements are translated into practical design rules for a representative CMOS technology. The minimum width and spacing rules for poly, active, and metal define the smallest features and separations that can be reliably fabricated. Contact and via dimensions, together with their enclosure requirements, provide sufficient process and alignment margin for reliable layer-to-layer connections. The table also shows that metal dimensions and density are constrained to support reliable interconnect fabrication and uniform processes such as CMP. These values should be viewed as illustrative rather than technology-specific PDK limits. The important concept is that each rule establishes a geometric constraint that the physical layout must satisfy. During DRC, these constraints are automatically checked to ensure that the layout remains within the manufacturing capability of the selected technology. After confirming that the layout follows the manufacturing design rules through DRC, the next important question is whether the layout actually represents the intended circuit. This is the purpose of layout versus schematic, or LVS. The physical layout is first converted into an extracted circuit netlist, which is then compared with the original schematic or reference netlist. LVS checks the presence and type of devices, their connectivity, transistor dimensions where applicable, and important power and ground connections. It can identify problems such as missing devices, extra devices, open connections, or unintended shorts. An important distinction is that a layout can be completely DRC clean and still fail LVS. DRC verifies manufacturability, whereas LVS verifies circuit correspondence. Therefore, DRC and LVS complement each other. DRC asks whether the layout can be manufactured, while LVS asks whether the manufactured structure represents the intended circuit. In this Part 1 presentation, we have reviewed the inherent constraints of a semiconductor fabrication processes due to material, equipment, and variations at different stages of manufacturing. These variations get translated into physical dimension variations, which affect device parameters and ultimately circuit performance, power, timing, and yield. The manufacturing limitations are therefore converted into design rules that define the permissible physical layout geometry. DRC verifies that the layout satisfies these manufacturing constraints, while LVS verifies that the layout correctly represents the intended circuit. In upcoming Part 2 video, we will have a review the fundamental principles of physical verification methodology of a layout design. Thanks for your time and hope to meet you in the upcoming video. Bye for now.